Welcome, dear participants, to our online series Medium Voltage Technology Essentials. My name is Pedro Gomez. I work as a Product Lifecycle Manager for air-insulated medium voltage switchgears, and today I am here with my colleague Miriam Johansson, who works as a Product Lifecycle Manager for gas-insulated switchgears.
I would like to share my personal motivation for creating this training with you. I've been working for Siemens AG since 2017. As a mechanical engineer, I switched from the agricultural and construction equipment industry to medium voltage technology, with which I had hardly any contact at that time. I would have appreciated a compressed basic training when I started. So, I'm more than happy to welcome you to this series.
The Medium Voltage Technology Essentials series comprises 7 informative videos, organized into 3 comprehensive blocks. My colleagues and I will guide you through the topics of power supply, components of a medium voltage switchgear, design criteria, construction of a switchgear, our medium voltage portfolio, as well as the current topics of digitalization and sustainability.
Should you have any questions during our series, please do not hesitate to use the Q&A feature located in the upper right corner of this platform. We will ensure that each question receives a detailed response via mail after the event. If you are in full screen mode and cannot see the Q&A field for questions or the chat box, simply press the escape key to exit full screen mode. Now, enjoy your journey on improving your knowledge of medium voltage technology.
And to conclude with the words of the Chinese philosopher Laozi, learning is like rowing against the current. If you stop, you drift back.
Hello everyone. Welcome to the next episode of our Medium Voltage Technology Essentials series. My name is Badri Narayanan Pattabhiraman. I am a Product Lifecycle Manager for gas-insulated switchgears at Siemens. It is a pleasure to have you all join us today, no matter where you are in the world. Building on the key design principles of switchgear covered in the previous sessions, today's session will explore the design aspects focusing on the structure, types, and applications of switchgear. Here is the agenda for this session. We will begin by examining the impact of switchgear structure, followed by a discussion on the aspects of type-tested metal-clad switchgear. Subsequently, we will explore the features and classifications of switchgears. The session will conclude with an overview on the basic structures of air-insulated and gas-insulated switchgears. Let's get started then. The first chapter is Impact of Structure of Switchgear. Let us analyze the medium voltage switchgears of yesterday and today. In this slide, we can see the differences between a switchgear of today depicted on the right side and that of the past depicted on the left side. One can see that the switchgears of the past had bigger dimensions in comparison to the compact and small dimensions of the present-day switchgears. This means the modern-day switchgears have smaller footprints and hence save space. Furthermore, the past switchgears are not protected well against the environmental conditions. In contrast, the switchgears of current are metal encapsulated, meaning that they are enclosed within a metal enclosure, providing certain degree of protection against environmental factors and mechanical impacts. Regarding personal safety, modern-day switchgears set a high standard contrary to those of the past, adhering to the safety regulations set in norms to prevent hazards and to ensure the safety of the user. Looking at the picture, one can say that the switchgears of the past require extensive maintenance efforts to keep them in good working condition, to avoid frequent repairs and downtimes. Meanwhile, the current switchgears require less maintenance efforts. Lastly, the switchgears of the past have high risks coming from arc failures and less fire hardness. On the contrary, Modern-day switchgears are tested according to the internal arc classification defined in the norms, setting specific safety standards. Here is a comparison of the switchgear structure based on the dimensions according to VDE 0101 standard against that of a type-tested design according to IEC 62271 standards. On the first column, you can refer to the features. The middle column refers to the VDE 0101 standards, and last column refers to IEC 62271 standards. In earlier times, in general, the design of switchgear was more component-oriented. In order to ensure certain dielectric strength, a minimum distance must be maintained for insulation capability as per VDE 0101 standards. Similarly, current capability is calculated based on current flow, conductor cross-section, etc. This also meant that the dimensions of former switchgears are very big in comparison to the compact design of current days. Today, switchgears undergo type testing in accordance with IEC standards, ensuring the design meets the requirements specified in IEC 62271, for example, in the form of dielectric tests and temperature rise tests. In the past, the interlockings were based on components used in design and almost not available. Today, these are tested as per standards. The same can be said for protection degree, which were only partly available in the past days, but are type tested at present. Another important thing is the protection against internal arc, which relates to the personal safety. The modern day switchgears are type tested to ensure that they are internal arc classified as per IEC standards. As touched upon previously, the modern day switchgears require less maintenance in comparison to the comprehensive maintenance requirements of former times. The quality and safety system, in short QS system, was not properly developed in former times. Today, this comprehensive framework ensures that high standards of quality and safety are maintained throughout the life cycle of switchgear. Finally, the documentation system of today is comprehensive with CAD design and details related to individual components, helping users with operation, installation, maintenance, etc. Such documentation was only partly available or even not available in the former times. Let us now proceed to the next chapter, which is metal-clad type-tested switchgear. Let us first examine the specifics of the switchgear enclosure, also known as encapsulation. The enclosure of the switchgear provides protection for the operators against touching live parts as well as in case of internal faults in switchgear as stated previously. Furthermore, it protects the devices against dust and humidity as well as prevents vermin such as rodents or small animals from entering or damaging the switchgear. The degree of protection, in other words, ingress protection, in short, the IP rating as defined by standards, indicates the degree to which an enclosure safeguards against the ingress of solid foreign objects and water. The enclosure provides a certain degree of protection against the mechanical impacts, which is defined by an IK coding. Now let us continue to the compartments of a switchgear. Let us speak in detail about the compartmentalization of a switchgear. A switchgear lineup can be subdivided into several individual panels, and each of these panels into many functional areas. In general, the compartments of switchgear are busbar compartment, switching device compartment, and cable connection compartment. Compartmentalization helps to enhance the reliability, safety, as well as the ease of maintenance. For example, a fault in one compartment can be contained without affecting other compartments. Similarly, repair works can happen in one compartment without shutting down the complete switchgear. Hence, in case there are many compartments, the faults can be limited within each compartment. At the same time, this would also mean that the access to the compartments is limited. On the other hand, if there are less compartments, the faults could extend, affecting other components as well. However, the accessibility to the components is increased. Let us now move on to the next chapter, features and classifications. The first topic is dielectric classification of partitions. In this slide, we will examine the two primary partition classes commonly employed in medium voltage switchgear. These are partition class PM, metallic partitions, M standing for metal, and partition class PI, non-metallic partitions, I standing for insulating material. The PM class is characterized by metallic partitions and shutters between live parts and opened compartments, and these metallic barriers are earthed. The basic features include the earthed metallic shields surrounding the opened or accessible compartments. Because metals are used, there are no problems concerning plastic. At the same time, this could lead to bigger dimensions. The PI class is characterized by the use of non-metallic partitions and shutters made of insulating materials between opened compartments and live parts. The quality of such insulating materials needs to be proved by extensive voltage test. Although construction is possible with compact design, this could lead to fire load because of isolating materials used. While both classes are designed to enhance safety, the PM class offers a higher level of protection compared to the PI class. However, the choice between them is based on the specific requirements of the installation. As the next topic, we will study the types of compartments. Let us now examine the non-accessible and accessible compartments of a medium voltage switchgear. On the left section, you can see a panel of a gas insulated switchgear. In this panel, the cable compartment at the bottom of the panel is depicted in a closed state. Further up, the closed area in the middle of the panel depicts the gas compartment which contains the switching device. This compartment is filled with gas and sealed for lifetime, meaning that the gas compartment is non-accessible after manufacturing. On the right side, you can see a panel of an air-insulated switchgear. The first picture from left shows the panel where the switching device compartment is closed. In the second picture, when the compartment is opened, there is a possibility to access the switching device, in this case, the withdrawable circuit breaker. In the third picture, when the circuit breaker is completely withdrawn outside, the shutter is closed and the compartment is fully accessible. Let's move on to the next topic, the LSC categories. LSC stands for the Loss of Service Continuity. It describes the extent to which the switchgear can remain in operation when access to a high voltage compartment is required. There are four main LSC categories as shown in the pictures on the slide. The first three are applicable for an air-insulated switchgear, and the last one on the right side for a gas-insulated switchgear. In the first picture on the left side, we see the category LSC1. Here, no service continuity is provided. Opening any accessible compartment requires the entire switchgear to be de-energized. On the extreme right, one can refer to the category LSC2, which is a category especially applicable for gas-insulated switchgears, allowing maximum continuity of service. For example, here it is possible to open the connection compartment while keeping the bus bars live. In case of LSC2A category, one can see in the picture that the bus bar compartment is segregated from the rest of the compartments, thus providing only a limited service continuity. Lastly, the category LSC2B provides the highest level of service continuity. Here one can see the three compartments, namely the bus bar compartment, switching device compartment, and the connection compartment separated. This category allows access to individual compartments without de-energizing the entire switchgear. These categories help to ensure safety and operational efficiency during maintenance and other activities. As the next topic, we will focus on the IAC classification in detail. IAC stands for Internal Arc Classification. The IAC classification is valid for switchgears which meet the prescribed criteria for protection of persons in the event of an internal arc. This is verified with internal arc fault test performed according to IEC standards. There are optional classifications, for example, regarding the arrangement of the switchgear being wall standing or freestanding arrangement. The test procedure to verify the internal arc classification is defined in the IEC standards. There are 5 prescribed acceptance criterions to pass the test. If IAC classification is assigned, then this designation is included in the nameplate of the switchgear. IAC designation on the nameplate. Let us investigate what is mentioned in the nameplate of the switchgears which are IAC classified. The classification IAC, as stated previously, stands for Internal Arc Classified. Types of accessibility. The types of accessibility are assigned to the switchgear after meeting the requirements stipulated in the IEC standards concerning test procedures and personal safety. The switchgears that are accessible to authorized personnel only have Type A designation. On the other hand, the switchgears that are accessible to the public are designated with Type B. The pole-mounted equipment is designated with Type C and are accessible to authorized personnel as well as general public upon satisfying appropriate requirements. Tested areas. F refers to the front side, L refers to the lateral side, and R refers to the rear side. Test values. The tested values are mentioned with current in kiloamperes, in short Ka, and duration in seconds, in short S. Let us look into 2 examples. In the example 1, IAC AFLR 25 Ka 1 second, one can refer to a switchgear which is internal arc classified with accessibility to authorized personnel on the front, lateral, and rear sides, and tested with a current of 25 kA and duration 1 second. In the example 2, IAC BF AR 16 kA 1 second, the switchgear is internal arc classified with front accessibility to public and rear accessibility only to authorized personnel and tested with a current of 16 kA and duration of 1 second. To conclude this chapter, let us explore some examples of IAC designation concerning the types of accessibility based on what we have learned. In the first picture on the left side, one can refer to a switchgear inside a building with type of accessibility A, meaning that the switchgear is accessible only to authorized personnel who wear personal protective equipment. The switchgears must satisfy the test requirements as stipulated in IEC standards. The picture in the middle shows a switchgear in a concrete substation in a city where the front, rear, and lateral sides of the station are publicly accessible with the type of accessibility B. The test requirements for type B as per IEC standards are different in comparison to type A. The main goal, however, is to ensure personal safety. The last picture on the right side shows a pole-mounted equipment with type of accessibility C, which could be accessed by both authorized personnel as well as general public while satisfying the corresponding safety requirements for personal safety. Now we have reached the final chapter, basic structure of air-insulated and gas-insulated switchgears. Let us learn about the basic design of gas-insulated and air-insulated switchgears. On the left side, you can refer to a gas-insulated switchgear, in short called as GIS, and on the right side, you can refer to an air-insulated switchgear, in short called as AIS. Let us start from the top. Here one can refer to the bus bars comprising the three phases which carry the current. This is followed by the disconnector and earthing switch. In case of GIS, this functionality is provided generally by a 3-position switch present inside the gas compartment. In case of AIS, the disconnection is provided when the shutters are closed, and the earthing functionality is provided by an earthing switch. Both GIS and AIS use vacuum circuit breakers, whose function, simply put, is to switch operating and fault currents. In case of GIS, the circuit breakers are also present inside the gas compartment. The gas compartment is then sealed for lifetime. In case of AIS, there is the possibility to withdraw the circuit breakers when opening the switching device compartment. As next, we have the current and voltage transformers. The current transformers, in short CTs, help in measuring and monitoring the electrical currents. They transform the higher currents to a lower current level, which can be used by protection relays to detect overcurrent and short circuit currents and perform protective actions. Additionally, the CTs can be used for bill metering and to measure energy consumption as required. Similarly, the voltage transformers, in short VTs or potential transformers, transform the high voltages into a lower level that can be used by protection relays or meters for protection and measurement purposes respectively. At the bottom part of the picture of gas-insulated and air-insulated switchgears, you can observe the cable connection compartment which helps in the termination of incoming and outgoing power cables. Let us now begin to wrap up the session by looking into the individual characteristics of air-insulated and gas-insulated switchgears. Characteristics of air-insulated switchgears. The air-insulated metal-clad switchgears AIS use air as the primary insulating medium and are cost-effective. The metal enclosure provides a certain degree of protection against environmental factors. At the same time, the switchgears are more vulnerable to external environmental conditions such as pollution, moisture, and saline environments. These factors could affect the dielectric strength of the switchgear. This can lead in some cases to issues like partial discharge, which can lead to overheating and to further failures. However, AIS has a lower environmental impact as it uses air as insulating medium. Because of the inherent dielectric characteristics of air, the AIS have comparatively larger dimensions in order to ensure proper isolating distances. The withdrawable part in the AIS helps to provide isolating distance, ensuring personal safety. The switchgears are easily accessible, especially for maintenance. However, because of the previously said reasons, AIS require regular maintenance to prevent the moisture and dust affecting the performance. Characteristics of gas-insulated switchgears. The gas-insulated metal-clad switchgears GIS use gas as the primary insulation medium. The insulating gas SF6 traditionally used has excellent dielectric properties but has impact on the environment because of it being a potent greenhouse gas. Because of this reason, Siemens is now moving to the next generation of environment-friendly gas-insulated switchgears which use the fluorine gas-free clean air technology. Let us now look into other characteristics of GIS. Since the primary parts are enclosed inside the gas compartment and hermetically sealed for lifetime, there is no influence from the environmental conditions. The probability of troubles caused by external influence are minimum, thus making them preferable for challenging climatic conditions. The GIS have designs with single pole as well as three-pole enclosure, meaning each pole individually or all three poles are encapsulated together in the gas compartment. The inherent excellent dielectric characteristic of gas helps in compact design of the switchgear. Moreover, GIS provides a maintenance-free design. When fulfilling the above listed condition, accessibility to the primary part is not necessary. We have now come to the end of this session. I appreciate your time and attention during today's session. We hope you gained valuable knowledge and enjoyed the session. If you have any further questions or need additional information, please don't hesitate to contact us. Stay tuned for our upcoming events. Have a great day.